So let's talk about how it is that stars form. So if you remember back when we talked about the sun, we said that the sun had two forces acting. First, we have gravity, which is pulling everything in, trying to crush everything down. And then we had pressure that's pushing out. That pressure is specifically gas pressure. Okay, so we have gas pressure pushing out and we have gravity pulling in. Well, if we want to take this large dispersed cloud and have it collapse down into a star, then gravity has to be greater than pressure. The force pulling in has to be greater than the force pushing out. Well, the place that it's most likely for this to happen are within molecular clouds or dark nebula. So if you remember, dark nebulae are relatively high density. Okay, so their densities are around 100 to 10,000 particles per meter cubed. That's high density for the interstellar medium. That's actually very low when we compare it to, say, the Earth's atmosphere. Okay, but for the interstellar medium, it's very high. And they have very low temperatures, around 10 Kelvin. The high density means we're going to have greater gravity. The low temperature means we're going to have low pressure. So it's within these dark nebula that stars are the most likely to begin to form. So in a typical dark nebula, these will contain a few thousand solar masses of material spread out over around 10 parsecs. Okay, that's somewhere around 33 light years across. Now the composition that we see for these is the same thing we've seen before, 74% hydrogen, 25% helium, and 1% everything else. Now, because of how big these are, it is likely that a single nebula will actually produce many stars. Because of this, they are sometimes referred to as stellar nurseries. Just like a nursery is the place where you keep the babies in a hospital, these are stellar nurseries because this is where all of the baby stars are located. Dark nebulae have enough mass for thousands of stars, and all of these stars will be forming at roughly the same time. This is where we get star clusters. Specifically, these are going to produce open clusters. Now at first, these pockets of gas that are going to be collapsing are going to be very dense and cold. Now because they are very, very cold, they're not going to be producing any light. Think back to the burner on an electric stove. Because it is cold, it does not produce light. However, as they contract, they begin to heat up. Now, as it continues to contract, it continues to heat up so that it's actually able to then begin convection. Okay, at this point where it's collapsing and it's starting to glow, now we refer to it as a protostar. Okay, a protostar is the thing that comes before the star or the thing that's on its way to being a star. Here is our third lecture quiz question. Where are cool but luminous objects found on the HR diagram? A, lower right, B, lower left, C, upper right, or D, upper left. Go ahead and think about it and we'll discuss in just a bit. Alright, so if it is cool but luminous, so cool things are on the right side of the HR diagram, but luminous things are near the top. Okay, so the correct answer is C. We expect these things in the upper right. So after a few thousand years, this protostar will have reached between 2,000 and 3,000 Kelvin. This is hot enough for it to begin to glow. But it's going to be relatively cool still. It's going to be over here on the red side. It's still too hot to touch. Don't try and swim in one of these things. But it's going to start over here on the right side. However, it hasn't contracted a lot, so it's still going to be very large, and because it's very large, it's going to have a relatively high luminosity. So we would actually expect these protostars to begin glowing in the upper right-hand corner on an HR diagram. Now, as these things continue to shrink, we start to have some interesting interplay. Okay, so depending on how fast they shrink, if they shrink really quickly, then they're going to heat up. If they shrink more slowly, then they're able to get rid of a lot of that energy so they don't actually heat up that much. Okay, but also, as they shrink, they're going to be smaller, which could lead to a drop in luminosity. But if they're also heating up, that could lead to an increase in luminosity. So we're getting all sorts of interesting interplays as these things shrink, depending on how long it's taking for them to shrink. Well, we can show all of these changes on the HR diagram. Okay, so the stars begin over here in the top right-hand corner. Then, as they shrink, depending on their mass, will determine which evolutionary track they're going to take. So right here, this very top track, this is a star around 15 solar masses. When it collapses, it doesn't really get that much more luminous. It does a little bit, but mostly it just heats up. So it just moves over to the left until it reaches the main sequence. Down here, at a half solar mass, this thing isn't really becoming that much hotter. It gets a little bit hotter, but not much. Mostly, it's just decreasing in luminosity, kind of falling down onto the HR diagram, until it hits down here. Now, other ones, like this one here at 1 solar mass and at 2 solar mass, have some interesting hooks and dips and bends and stuff, but all this is showing us are changes in the luminosity and temperature as these stars are collapsing. Now, after a while, once the core of these stars have reached 10 million Kelvin, then they're able to begin hydrogen fusion. Before they begin hydrogen fusion, they are protostars. Once we have sustained ongoing hydrogen fusion in their core, they have now reached the main sequence and are not now full-fledged stars. Now, these protostars are still going to be embedded within the overall dark nebula, which means we're not going to see them. At least we're not going to see them using visible light. The dark nebula blocks visible light. However, the interstellar medium is actually transparent to infrared light. So we can't see it using visible light, but when we look in the infrared into these dark nebula, then we can actually see these protostars in the process of forming. Now, as these stars form within the nebula, they're actually very, very chaotic. They can both gain and lose mass during this process. There's one type of protostar called a T Tauri, which is located in the constellation of Taurus, which has less than 3 solar masses, and we actually see it change brightness because of mass loss. Okay, so as we watch these things, they actually fluctuate brightness as they are losing material back out into the nebula. Over the formation process, these T Tauri stars can actually lose up to 1 solar mass of material, an entire sun's worth of material. Now, we believe that protostars above 3 solar masses, which are not classified as T Tauri, do not change in brightness, but they still have the same overall mass ejection. Now, we've actually seen that some very young stars actually produce outflow through narrow jets. So, for example, in this image, right here in the center, this is a dark nebula, and we do not see the protostar because it's embedded inside. However, the jets from this star are shooting out and then colliding with the interstellar medium, causing a lot of friction, creating energized gas, which we can then see. So we get this jet outflow. Now, this sort of jet will only last from 10,000 to 100,000 years. And I realize that sounds like a long time, but consider how long stars last. If we're looking at stars that last for billions of years, 10,000 really isn't that long. As these protostars are still within the nebula, they can also still be gaining mass, having material fall down onto them from the nebula. So here we have a circumstellar accretion disk. This is material that is orbiting, circling around, and some of it may be falling onto the star. But then here we have the jets that are causing an outflow away from the star. So while these stars are still embedded in the overall nebula, it's actually a highly chaotic time.